This work presents and demonstrates natural multi-contact working for robotic assistive devices via musculoskeletal models and hybrid aerodynamics. The goal of this work is to translate natural and efficient human locomotion to robotic assistive devices by generating provably stable walking gaits through the hybrid aerodynamics method of gait generation, with musculoskeletal models directly embedded into the optimization problem. We demonstrate our proposed framework towards achieving multi-contact locomotion on the AMPRO3 dual-actuated prosthesis, and construct the hybrid system to include 8 distinct domains and 8 edges. Since the constraints in the optimization problem are often tuned in order to achieve desired behavior, we leverage preference-based learning to systematically identify the constraints that lead to the most natural gait for fair comparison between gaits generated with and without the inclusion of the musculoskeletal model. To evaluate naturalness, we used a custom metric called gait RMSE, which essentially assesses how close the generated gaits are to the joint trajectories from motion capture data. Throughout the systematic tuning process, the inclusion of muscle models lead to a smaller gait RMSE compared to the gaits generated by the non-muscle version. This process was repeated for 2 subjects. The 2 best final gaits were then executed on the AMPRO3 prosthesis. The non-disabled subject's electromyography activity was also recorded during the experiments using surface mount electrodes. These wireless sensors were placed on 4 muscles of the non-prosthetic leg and 2 side muscles of the prosthetic leg of the user. The subjects were blindly given 2 gaits and were provided enough time to adjust to each gait till they feel comfortable working with them. Both subjects would strongly prefer the gaits generated with the inclusion of muscle model. The RMSE of electromyography recording indicated that the addition of the musculoskeletal models resulted in a closer muscle activation pattern to that of normal walking between the 2 tested prosthetic gaits. Future work include extending this method to higher dimensional platforms such as a full lower body exoskeleton and generating gaits with desired muscle activation pattern. In summary, this framework provides a non-data-driven method towards generating stable and natural multi-contact locomotion.